Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual edifice of late 19th century physics finds one of its most ambitious and consequential expressions in Ludwig Boltzmann's crowning synthesis, the Lectures on Gas Theory, published in 2 parts culminating near the end of the century. This work represents the definitive articulation of the atomistic hypothesis as a powerful explanatory framework for the phenomena of thermodynamics. It is a text of immense architectural complexity, a sustained argument that seeks to derive the empirical laws of heat and energy from the purely mechanical interactions of a vast multitude of unseen particles. This essay undertakes a rigorous evaluation of the specific claims advanced within this monumental work, proceeding section by section to analyse the internal logic, the methodological innovations, and the profound conceptual leaps that characterise Boltzmann's programme. We will examine the very sinews of his arguments, assessing the foundations upon which he constructed a statistical interpretation of the physical world, a move that would fundamentally reconfigure the nature of scientific law itself. Section 1. The foundational postulates of an atomic world. Boltzmann commences his lectures with a set of foundational postulates that are both audacious in their simplicity and profound in their implications. He posits a model of a gas as a collection of an immense number of discrete, perfectly elastic material points, or molecules, engaged in perpetual, chaotic motion within a fixed volume. The central claim here is that the entirety of the observable thermodynamic properties of a gas can be explained and predicted from the mechanical behaviour of these constituent parts. In evaluating this initial step, we see Boltzmann employing a powerful idealization. He specifies that the volume occupied by the molecules themselves is negligible compared to the total volume of the container, and that forces between molecules are effective only during the infinitesimally brief moments of collision. This framework, inherited and refined from the earlier kinetic theorists like Clausius and Maxwell, is presented as a necessary starting point for rendering the problem mathematically tractable. The argument's strength lies in its strategic reductionism. By asserting the primacy of Newtonian mechanics at the microscopic level, Boltzmann claims the authority of classical dynamics for his new domain. He then introduces the pivotal concept of the velocity distribution function, a mathematical object represented as f of v, t, which describes the probable number of molecules per unit volume that possess a certain velocity at a given time. This move is a profound shift in descriptive strategy. The state of the gas is henceforth characterized by a statistical distribution, a holistic property of the ensemble, thereby foregoing an impossible attempt to track the trajectory of each individual particle. The claim is that this statistical snapshot contains all the necessary information to determine the macroscopic state of the system. Boltzmann's justification for this is pragmatic and powerful. It is the only viable path to connect the microscopic and macroscopic realms. Section 2. The collision integral and the emergence equilibrium. Having established a statistical representation of the gaseous state, Boltzmann proceeds to one of his most crucial arguments, the derivation of the equilibrium distribution of molecular velocities. His central claim is that through the mechanism of intermolecular collisions, any arbitrary initial velocity distribution will inevitably evolve towards a specific, time-invariant form, which is the Maxwell-Boltzmann distribution. The engine of this argument is the famous Stossel-Ansatz, or the assumption of molecular chaos. Within the text, this is presented as a physically intuitive hypothesis. Boltzmann argues that for any given collision between 2 particles, their incoming velocities are entirely uncorrelated. He claims that in a sufficiently dilute gas with random motion, the probability of finding 2 molecules with specific velocities in the same region of space, about to collide, is simply the product of their individual probabilities. Evaluating this claim reveals it as the arguable linchpin of his entire deductive structure. It is a statistical postulate masquerading as a mechanical one. Boltzmann's derivation involves setting up a complex integral differential equation today known as the Boltzmann transport equation, which describes the rate of change of the distribution function over time. The equation balances the number of particles entering a given velocity range due to collisions against the number leaving it. He then demonstrates that the distribution function ceases to change only when a specific condition is met, leading directly to the exponential form of the Maxwell-Boltzmann distribution. The persuasive power of this derivation within the lectures is immense. It provides a concrete, mechanical narrative for the process of thermalization, showing how a system, left to itself, achieves a stable, uniform state. The claim is that equilibrium is a dynamic, statistical steady state, a concept of profound elegance. The internal logic is compelling, provided one accepts the foundational Stossalansatz without immediate objection. Section 3. The mechanical basis of thermodynamic properties. Following his derivation of the equilibrium state, Boltzmann advances the claim that the macroscopic, observable properties of a gas, specifically its pressure and temperature, are direct mechanical consequences of the microscopic motions of its constituent atoms. This section of the lectures forges the definitive link between the kinetic theory and classical thermodynamics. His argument concerning pressure is a masterpiece of mechanical reasoning. He claims that the pressure exerted by the gas on the walls of its container is the result of the continuous transfer of momentum from the colliding molecules to the wall. He calculates the average force exerted per unit area by considering the number of particles striking the wall per unit time and the average momentum they impart. The brilliance of the claim lies in its ability to translate a chaotic, microscopic bombardment into a constant, uniform macroscopic force. Similarly, Boltzmann makes the profound identification of absolute temperature with the average kinetic energy of the molecules in the system. The claim is that the thermodynamic concept of temperature, previously understood only through empirical scales and its role in heat flow, has a precise mechanical meaning. Evaluating this, we find the powerful act of conceptual unification, the ideal gas law. Pressure times volume equals a constant multiplied by temperature, ceases to be a mere empirical relation. In Boltzmann's framework, it becomes a theorem derived from first principles. He demonstrates with mathematical rigor how, by substituting the mechanical definitions of pressure and temperature into the equation, the law emerges as a direct consequence of the statistical mechanics of the molecular ensemble. This part of the lectures represented a decisive victory for the atomistic program, offering a compelling, mechanistic explanation for one of the cornerstone laws of physical chemistry. Section 4. The H-theorem and the statistical arrow of time. Perhaps the most celebrated and philosophically charged section of the lectures is part where Boltzmann introduces his H-theorem. The central claim here is that a specific quantity, which he designates H, must, for any isolated gas system not in equilibrium, decrease monotonically over time until it reaches a minimum value, at which point the system is in its state of equilibrium. He defines the quantity H as the integral, over all possible velocities, of the product of the distribution function, f of v, and the natural logarithm of that same distribution function. The argument he presents is a mathematical proof based on his transport equation. He shows that the time derivative of h, dh divided by dt, is always less than or equal to 0. The genius of this claim is that it purports to provide a mechanical foundation for the second law of thermodynamics, the irreversible increase of entropy, the property that gives time its arrow and forbids processes like heat flowing spontaneously from a cold body to a hot one, is identified with the monotonic decrease of his H function. Evaluating this claim, however, exposes the deep philosophical tensions at the heart of his project. The H-theorem derives an irreversible, time-asymmetric result from the underlying laws of Newtonian mechanics, which are themselves perfectly time-reversible for any collision process. The reverse process is dynamically possible. The internal logic of the proof rests, once again, entirely on the Stossalansatz, the assumption of molecular chaos, which seems so innocent when establishing equilibrium, reveals itself here as a time-asymmetric postulate. It assumes particles are uncorrelated before they collide, a condition that implicitly injects a direction of time into the system from the outset. Boltzmann, in the lectures, presents the theorem as a rigorous mechanical deduction, a stance that would invite powerful critiques. Section 5 reversibility objections and the probabilistic reinterpretation. Boltzmann, a thinker acutely aware of the philosophical ground he was treading, engages directly with the profound challenges to his H-theorem. A core claim that evolves through the later sections of his work is that the second law of thermodynamics, and by extension his H-theorem, must be understood as a statistical or probabilistic law, a statement about overwhelming likelihoods. This evolution in his argument is prompted by objections like that of his contemporary, Joseph Loschmidt, who formulated the reversibility paradox. Loschmidt argued that if one could magically reverse the velocities of all particles in a gas at a given moment, the system should, according to the time-reversible laws of mechanics, retrace its steps, leading to a state where h increases. This would violate the H-theorem. Boltzmann's response within the lectures is a masterstroke of reinterpretation. He concedes the logical possibility of such an antithermodynamic evolution. His revised claim is that while such states are mechanically possible, they are stupendously, vanishingly improbable. He argues that for any given macrostate, characterized by properties like pressure and temperature, there exists a colossal number of corresponding microscopic arrangements of particles, or microstates. He claims that the number of microstates corresponding to the equilibrium state, the one with the Maxwell-Boltzmann distribution, is so vastly greater than the number corresponding to any non-equilibrium state that the system's spontaneous evolution towards equilibrium is a practical certainty. Evaluating this probabilistic turn, we witness a fundamental shift in the nature of a physical law. Boltzmann is effectively claiming that the second law is a law of averages, a principle of statistical mechanics. The system does not evolve towards equilibrium because it is forced to by a deterministic law, but because it is overwhelmingly likely to. An ordered, low-entropy state is not impossible. It is a configuration of particles of infinitesimal probability, analogous to finding all the air molecules suddenly gathered in one corner of a room. This probabilistic framework is Boltzmann's ultimate defense and his most enduring legacy. Section 6 the combinatorial foundation of entropy. In the final stages of his argument, Boltzmann deepens his probabilistic claim by connecting it to a combinatorial foundation. The ultimate claim of the lectures is that the thermodynamic quantity of entropy is directly proportional to the logarithm of the number of ways a macroscopic state can be realized at the microscopic level, while the famous equation, entropy S equals Boltzmann's constant k times the natural logarithm of the number of microstates W, is more famously associated with a later inscription on his tombstone. The entire conceptual apparatus is laid bare in the lectures. He claims the state of equilibrium is the most probable state because it possesses the largest number of possible combinatorial arrangements of molecular positions and velocities consistent with the system's total energy. The increase of entropy is thus reconceptualized as the system's natural tendency to move from a less probable, more specially ordered configuration to a more probable, more disordered one. In evaluating this claim, we see the culmination of his entire program. The mysterious, abstract concept of entropy is rendered tangible and calculable through the counting of atomic configurations. This provides a powerful, intuitive picture of the second law. A deck of cards, when shuffled, moves from an ordered state to a disordered state simply because there are vastly more disordered arrangements than ordered ones. Boltzmann claims the same principle governs the universe at a fundamental level. The internal coherence of this final argument is profound. It provides a satisfying resolution to the paradoxes of irreversibility by grounding the second law in the logic of combinatorics and probability theory. It transforms thermodynamics from a science of phenomenological principles into a branch of statistical mechanics, a move that required a complete rethinking of what it means for a physical theory to be. Conclusion: Ludwig Boltzmann's lectures on gas theory stands as a work of singular intellectual power and ambition. The evaluation of its internal claims reveals a meticulously constructed argument that builds, layer by layer, from a simple mechanical model of atoms to a profound statistical interpretation of the fundamental laws of nature. His initial claims about the atomic nature of gases and the statistical description of their state provided a tractable and powerful foundation. The subsequent derivation of equilibrium and the mechanical basis for pressure and temperature demonstrated the immense explanatory power of the kinetic theory, fulfilling the promise of the atomistic worldview. The centerpiece of the work, the H-theorem, while mathematically elegant, rested on the pivotal and controversial Stossel ansatz, forcing a confrontation with the deep problem of irreversibility. It was in his response to these challenges that Boltzmann made his most enduring contribution. By recasting the second law as a probabilistic principle, he fundamentally altered the epistemology of physics. The claim that entropy is a measure of molecular disorder, quantifiable through combinatorial analysis, provided a definitive and deeply intuitive explanation for the arrow of time. The lectures, therefore, represent a complete intellectual journey, one that begins with the confident application of classical mechanics and concludes with the revolutionary introduction of statistical reasoning as an indispensable tool for understanding the physical world. The work is a monument not only to the success of atomism, but to the power of a single mind to grapple with the deepest paradoxes of nature and, in so doing, to forge the conceptual foundations for the physics of the 20th century.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.